Uh, Hello, can you guys hear me?
Yes, sir, we can hear you.
Yes, sir.
Uh, Great. So I'll be sharing my screen now, and just confirm if you are able to see the screen. Just a second. Uh, yeah. So are you able to see the OneNote page that I'm currently on?
Yes, sir.
Okay. So today will be a short session, kind of short, because the programming problem that we gave in week 7 was kind of easy. Because in the last few sessions, the problems were like really tough, as people told me. So we kept it a bit easy for week 7. And the problem is as follows. I'll continue reading the problem. So there's a story and all, but the main thing that the problem is asking is you'll be given a set of cities and there will be some roads between these cities. So there can be even multiple roads from like a city to another city. And what you want to do is you want to yeah. So you want to tell the maximum length of the road that you can break. And after you break the road, you would want all the cities to be connected. So you would want everything to be connected to be stay connected. And is there other condition? There might be some cities, multiple roads. Okay, the length of the total road should be as high as possible. Yeah, so this condition also. So length, you have to maximize the length also. So the length of the total road broken should be as high as possible. So yeah, so these two conditions, you have to break roads in such a way that after breaking the roads, the every city is still connected by a network of roads to another city. And by connection, I mean if we say this city and this city is connected, by that I mean there's a path from this particular city to the other city where we use some particular road. So yeah, these two cities that I marked with blue over here, they are connected by the same logic. And yeah, so everything should be connected, and the length of the broken road should be maximum. So uh, it's kind of giving you a feeling of a minimum spanning tree because so in a minimum spanning tree, it's a tree that we form from a graph in which every node is connected. So the actual minimum spanning tree is a tree in which every node is connected to another node through a set of edges, and may not be directly connected, but we can have a simple path from one particular node to another particular node, and the sum of the weights is minimum. Yeah. So, you guys have any idea, or you want to share your approach, like how you approach this problem? You guys can see the screen, right? Listen, like, able to listen to me. Just drop a yes in the chat if you can, like, listen to me and see the screen, like everything I'm writing down on the screen. So, yeah, you can see. Yeah, so I'll discuss the approach that I used. And what I did was, let's say I have a graph like this. Or maybe I'll give you like a minute to think about the approach and then maybe we can discuss the approach. Yeah, just take a minute to think about the approach. In a minute, I'll just go over what my approach is. I'll just move over the screen to the problem if you want to read the problem again. And yeah, in about a minute, we can start discussing the solution. Yeah, so some of you might have heard about the solution, which might be different from the solution, and you are free to discuss that here just after I finish discussing this. So we want to break some roads, and we want the length of the total road to be broken as maximum as possible, and we want the remaining roads in such a way such that the network, or you can say a graph that is remaining after we remove some edges, is still connected. So you can think it as something like this. So in an MST, you have certain edges and nodes in such a way that the sum of the weight of the edges is minimum. And you can think of it in such a way that after you break some roads, the remaining number of roads. So you want the length of the broken road to be maximum. So the length of the broken road uh, plus the length of the remaining roads is constant, right? So it's the sum of all the roads. So either a road could be broken or it's remaining. So when you sum these up, you get a constant that is given to you in the question. So if you bring this to the right side. So length of the remaining roads is a constant C, or let's say N, minus length of broken road. And when you want to max, just a second. Yeah, when you want to maximize this, what you're doing is basically you're minimizing this whole thing. So you're minimizing the length of the remaining road. So you can think of it as an MST, because the length of the remaining road is basically the sum of the weight of the edges of the remaining road, and you want to have it as minimum as possible. So what you would want to do is you would want to find an MST of this graph, and you would say that this particular MST is the network of remaining roads, and all the rest of the roads that are not present in the MST, or the edges that are not present in the MST, we are breaking these off. So let's say if this green thing is the network that we finally got, so we'll be breaking these particular roads out. Because as we have formed an MST, we are sure that this thing satisfies. Length of some of the length of the remaining edges is minimum. So we can for sure say that the length of the broken edges from the graph would be maximum. So I'll just go over through the code, and maybe after that you can ask if you haven't done. So I am storing these edges in a way such that I'm having the weight. So the structure is somewhat like this. I'm having the weight first, and then I'm having U and V. So U and V are the end point of this particular edge, and W is the weight of this edge. Yeah, and then I have N as the number of nodes and M as the number of edges. I take them as input. Total is the total length of the edges that I receive. So what I represented here as N, I'm calling here total. So then I run a for loop from 0 to n because I want to take all the edges as input. I take these as input, and I push these into this particular vector that I made for storing these edges. And I increment total by W, because the weight of this particular edge is W, and for total I'm counting the total weight of all the edges. So I push the this particular edge in this vector, and I increment total by W. Then I initialize my DSU. So you guys had DSU in a previous week, and for Crystal's algorithm, I in my particular implementation I use DSU. So Yeah, that's how I solved it. So I initialized the DSU. I sort the edges, and as I haven't written any custom comparator here, uh, so no custom comparator. That means these edges would be sorted by weight because weight is the first component here. And if the weight is same, then we'll see this. But for our particular use case, the only thing that we care about is it sorts these particular edges by weight, and it does sort by weight because W is the first element in this struct. So and yeah, so then what I do is I basically use the Crystal algorithm to find the cost of the minimum spanning tree, cost of making the minimum spanning tree, where cost is the sum of edges in the minimum spanning tree from MST. And after I find this particular cost, so the cost is the thing that I'm representing here by green. So W1, W2, 4, 5, 6. So yeah, so cost is basically these 1, 2, 3, 4, 5, and 6. So I subtract this particular value from the total value, which leaves us with the sum of these particular weights of these values. And that's the answer that we are looking for. So we wanted to break roads such as the length of the road that we broke was maximum. That means the length of the road that is remaining should be minimum, and the network should still be connected. So that's what an MST is, and yeah, we use the MST properties and the algorithm, Crystal algorithm for finding it. So if you guys have any doubt, you can uh, ask, or maybe if you want to share your own approach, which was different or maybe similar from this, you can share also. Okay, great. So I think nobody has any particular doubt with this problem. So yeah, this time we had a bit easier problem than previous weeks because we received some feedback that the problems were a bit difficult. But again, from next week, I think we'll have more difficult problems than this particular one. This particular one was, if you understood the question and maybe grasped that what we wanted was basically an MST because we wanted the length of the road that is remaining to be minimum. So if you had thought of MST there, you would have easily solved the problem. Yeah, so this problem was easy with implementation, but again, you would have to think it in terms of MST, and then only you would have solved this problem. Great. So if nobody has doubt, maybe we can close this session again. If someone has doubt, I'll wait another few minutes for you guys to maybe grasp what I've just told, or maybe list out some of the doubts. For that particular session with the professor, I'm not really sure about that. Maybe I'll get back to you. Like, are you in the Discord server for this particular course? Okay, yeah. So most of the communication that we do, like apart from the official announcements, the doubt clearing or maybe some of the discussions for the various problems, is generally done in that Discord server. And like you can also tag, like you can also communicate with the professor there also. So you can find Nindra ma'am in the Discord server. Uh, the link of the Discord server. Okay, I'll share the link. Yeah, I'll share the link in the chat box. Just give me a second. Yeah, so this is the link from the Discord, like the invite link for the Discord server, and you can join using this. So looks like nobody. Okay, have a good command over Arish since we will start, but I have no idea what to practice and couldn't graph. So for practicing graph entry problems, what I did when I was practicing was I opened Geeks for Geeks and they had a practice session and I just practiced like the easiest problems from graphs entries. Firstly, I practiced all the easier problems like 2 to 3 times to get hold of the implementation of basic DFS, DFS traversals, and then for trees, we generally do a recursive DFS. So to get grasp of like basically getting comfortable with these particular algorithms, writing down these algorithms, modifying these algorithms, I used to solve very easy problems. After solving around 20 easy problems, I moved on to online judges like Courses and CodeChef, and then I solved problems there. And yeah, they have different tags for problems. So there's a tag for tree problems, there's a tag for DFS graphs, and shortest path problems. And yeah, you can solve using those tags. Okay, so looks like nobody else has any doubt. So maybe we can close up this session and we'll meet you guys in the next discussion session for the next week problems. Thank you.